Hello student, welcome to my lecture paper number 13 functional analysis 2. Myself Hardik Ampandia, research scholar Department of Mathematics, Maharaja Krishna Kumar Singhji, Bhavnagar University, Bhavnagar. Theorem: if A is Banach subalgebra of A, Banach algebra A dash. If A is Banach subalgebra of a Banach algebra A dash, then sigma A dash of x is subset of sigma A of x. And second, boundary of sigma A of x is subset of boundary of sigma A dash of x. Proof: let lambda belongs to sigma A dash of x. So x minus lambda into 1 is singular in A dash. So x minus lambda into 1 is singular in A because A is subset of A dash. So, lambda belongs to sigma A of x. Lambda we have taken lambda belongs to sigma A dash of x, and we get lambda belongs to sigma A of x. So sigma A dash of x is subset of sigma A of x. First is complete. Now lambda belongs to sigma lambda belongs to boundary of sigma A of x. Now sigma A of x is equal to lambda belongs to C such that x minus lambda into 1 is singular in A. So x minus lambda into 1 is boundary point of the set of singular point in A. We know that boundary of singular points is subset of Z. So x minus lambda into 1 is topological. X minus lambda into 1 is topological divisor of 0 in A. So x minus lambda into 1 is topological divisor of 0 in A dash. So x minus lambda into 1 is singular in A dash. So lambda belongs to sigma A dash of x and lambda belongs to its closure. Equation number 1. Now we show that lambda belongs to closure of script C of sigma A dash of x. That is to show that lambda belongs to, this is complement of sigma A dash of x. So we can write C minus sigma A dash of x closure. We have lambda belongs to boundary of sigma A of x. So lambda belongs to sigma A of x closure intersection closure of its complement. So lambda belongs to closure of C minus sigma A of x. What is boundary? Boundary means uh, boundary point which is not interior and exterior. It is called boundary point. Now sigma A dash of x is subset of sigma A of x. So sigma A dash of x is equal to C minus sigma A of x is subset of C minus sigma A dash of x. Now take its closure because A is subset of B implies A closure is subset of B closure. So we can write this equation number 3. From equation number 2, From equation number 2, lambda belongs to this and this is subset of this. This is subset of this. So lambda belongs to this. Lambda belongs to closure of C minus sigma a dash of x. Equation number 4. From equation number 1 and 4, equation number 1, lambda belongs to closure of sigma a dash of x and lambda belongs to closure of C minus sigma a dash of x. So lambda belongs to intersection of both. So lambda belongs to boundary of sigma a dash of x. જો કોઈ point lambda belongs to a હોય and lambda belongs to b હોય તો lambda belongs to a intersection implies lambda belongs to a intersection b. So from a and b we get boundary of sigma a of x is subset of boundary of sigma a dash of x. Note, lambda belongs to boundary of z implies lambda belongs to its closure intersection closure of its complement. Now definition, spectral radius of x. Definition, spectral radius of x. Let A be Banach algebra and let x belongs to A be Banach algebra and let x belongs to A, then the spectral radius of x is defined by r of x is equal to supremum of mod lambda, where lambda belongs to sigma a of x. It is clear that r of x is less than or equal to norm x. Lemma. Let A be a Banach algebra and let x belongs to A, then r of x raised to n is equal to r of x raised to n. Also we can prove sigma of xn is equal to sigma of x raised to n. Let lambda 1, lambda 2 up to lambda n be nth root of non-zero complex number lambda, then x raised to n minus lambda into 1 is equal to x minus lambda into 1 into x minus lambda 2 into 1 plus up to x minus lambda n into 1. If x raised to n minus lambda into 1 is regular, then each x minus lambda into 1, x minus lambda 2 into 1 up to x minus lambda n into 1 is regular. If x raised to n minus lambda into 1 is regular, then all its factors are regular. If x raised to n minus lambda into 1 is singular, if and only if at least one of them is singular. Now lambda belongs to sigma x raised to n if and only if x raised to n minus lambda into 1 is singular, if and only if x minus lambda I into 1 is singular in A for some I belongs to 1 to n, if and only if lambda I belongs to sigma x if and only if lambda I raised to n belongs to sigma x raised to n implies lambda belongs to sigma x raised to n. Hence, sigma x raised to n is equal to sigma x raised to n. First is proof, and this implies this implies r of x raised to n is equal to r of x raised to n. Hence the theorem. Now the next theorem, let A be a Banach algebra and let x belongs to A, then R of x, spectral radius formula, R of x is equal to limit n tends to infinite norm x raised to n raised to 1 by n. This is spectral radius formula proof. We know that R of x is less than or equal to norm x, and R of x raised to n is less than or equal to norm R of. Now we take x is equal to x raised to n. So R of x raised to n is less than or equal to norm x raised to n. Here R of x is less than or equal to norm x. We take x is equal to x raised to n. So R of x raised to n is less than or equal to norm x raised to n. But by above theorem, R of x raised to n is equal to R of x raised to n. So R of x raised to n is less than or equal to norm x raised to n. This is by above theorem. So now square root root लिए तो R of x is less than or equal to norm x raised to n raised to 1 by n. So R of x is less than or equal to limit n tends to infinite norm x raised to n raised to 1 by n. Equation number 1. First, we shall prove that if a is any real number with R of x is less than a, then norm x raised to n raised to 1 by n is less than or equal to a for all but finite number of n's. This is sufficient to prove for reserve reverse inequality. This is sufficient to prove reverse inequality. So because of R of x is less than R of x plus positive integer epsilon greater than 0. So this this is equal to norm x raised to n raised to 1 by n is less than or equal to R of x plus epsilon. Epsilon is greater than 0. This is true for every arbitrary smallest positive number epsilon. So limit n tends to infinite norm x raised to n raised to 1 by n is less than or equal to R of x. Suppose mod lambda is greater than norm x. So x minus lambda into 1 inverse exists. Let x lambda is equal to x minus lambda into 1 inverse. Now common out lambda, so we get lambda inverse into x upon lambda minus 1 inverse. And now common out minus, so minus lambda inverse into 1 minus x upon lambda inverse, and simplifying this by by previous lemma 1 minus x inverse. So we get 1 plus summation n is equal to 1 to infinite x upon lambda raised to n by this. So x lambda is equal to minus lambda inverse 1 plus summation n is equal to 1 to infinite x raised to n upon lambda raised to n. Equation number 2. Let f belongs to a star. So f is continuous linear transformation from a to c. Then from 2 we have f of x lambda is equal to minus lambda inverse f of 1 plus summation n is equal to 1 to infinite f of x raised to n into lambda raised to minus n upon lambda raised to n. So we write in multiplication, so lambda raised to minus n. Equation number 3. We know that f of x of lambda is an analytic function in the region mod lambda is greater than r of x. Since 3 is equation 3 is the Lorentz expansion series for mod lambda is greater than norm x. This expression is valid for mod lambda is greater than r of x. If we now let alpha be any real number such that r of x is less than alpha less than a, then the series summation n is equal to 1 to infinite f of x raised to n upon alpha raised to n converge. So the term of this convergence series from a bounded sequence, since this is true for any f belongs to a star elements x raised to n upon alpha raised to n from a bounded sequence. So norm x raised to n upon alpha raised to n is less than or equal to k for some positive integer k. So norm x raised to n is less than or equal to k. Norm x raised to n is less than or equal to k into alpha raised to n, and alpha is greater than or equal to 0. So norm x raised to n, and now take the root, nth root. So norm x raised to n raised to 1 by n is less than or equal to k raised to 1 by n into alpha. Since k raised to 1 by n into alpha is less than or equal to a for all but a finite number of n. So norm x raised to n raised to 1 by n is less than a. Because of this is less than a, so norm x raised to n raised to 1 by n is less than a. This is complete the proof. Now definition ideal. Let A be Banach algebra and ideal I of A is subset of A with the following properties are satisfied. I is a linear subspace of A, I belongs to I, and X belongs to A implies X into I belongs to I, and I belongs to A, X belongs to A implies I into X belongs to A. First condition and satis first and satis first and second condition satisfy, then I is called left ideal. First and second condition satisfy, then I is called left ideal, and first and third condition satisfies, then I is called right ideal of A. Definition regular. Left regular, an element x belongs to A is called left regular if there exists y belongs to A such that y into x is equal to 1, and an element x belongs to A is called Write regular if there exists y belongs to A such that xy is equal to 1. Not if x is both left and right regular, then left inverse and right inverse of x are same. Let y is left inverse of x and z is right inverse of x, then y is left inverse of x, so y into x is equal to y into x is equal to 1 and x into z is equal to 1. Now y is equal to y into 1 and 1 is equal to, we take x into z. So by associative property, y into x into z, now y into x is equal to 1, so 1 into z is equal to z, so y is equal to z. We prove the statement. Now definition, maximal ideal. An ideal M of A is said to be maximal ideal or maximal left ideal of A if there is no ideal I such that M, M is proper ideal of M, proper subset of I, proper subset of A. Not if I is an ideal of A, then by John's lemma there exists a maximal ideal in A. Definition, radial. The intersection of all maximal left ideal of a Banach algebra A is called radial of A. The intersection of all maximal left ideal of a Banach algebra A is called radial of A. It is denoted by R. R is equal to intersection of all maximal left ideal of A. Obviously, R is a proper left ideal of A. If an ideal I of A contains unity, then I is equal to A. If an ideal I of A contains unit element, then I is equal to A. Lemma, if R belongs to R, then 1 minus R is left regular. Proof, if possible, suppose 1 minus R is left singular. We suppose here contradiction. Let L is equal to A into 1 minus R is equal to X into 1 minus R such that X belongs to A. Then L is a proper left ideal of A which contain 1 minus R. Claim 1 is not belongs to L. Uh, Here we suppose if 1 belongs to L, then there exists y belongs to A such that y into 1 minus R is equal to 1. So 1 minus R is left regular, which is contradiction to fact that by John's lemma there exists a maximal left ideal M of A such that L is subset of M. So 1 minus R belongs to M. Since R belongs to R implies R belongs to M. So 1 belongs to M and 1 belongs to M. So by not 1, m is equal to a. This is not possible because m is proper left ideal. Hence 1 minus r is left regular. This is complete the proof. Now lemma 2, if r belongs to R, then 1 minus R is regular. Let R belongs to R implies 1 minus R is left regular, implies there exists S belongs to A such that S into 1 minus R is equal to 1. So 1 multiply करिए तो 1 minus S minus S into R is equal to 1. So this આ term ને આ બાજુ લઈએ તો S is equal to 1, S is equal to 1 plus S into R. So we can write 1 minus of minus, minus multiple માં હોય ત્યારે plus થઈ જાય. So 1 minus of minus S into R. Now R belongs to R and minus S belongs to A implies minus S into R belongs to R because R is left ideal, implies 1 minus, so 1 minus of minus S into R is left regular, implies S is left regular. Since S into 1 minus R is equal to 1 and S is right regular, so S is regular. So S into 1 minus R is equal to 1 minus R into S is equal to 1. So 1 minus R is regular. This is complete the proof. Lemma 4. 3. If R belongs to R, then 1 minus X into R is regular for each X belongs to A. Let R is left ideal, so R belongs to R and X belongs to A implies X into R belongs to R, implies 1 minus XR is regular by lemma 2. Hence the complete the proof. Lemma 4. If R is an element of A with the properties that 1 minus XR is regular for all X belongs to A, then R belongs to R. Now we suppose R is not belongs to R. So R does not belongs to M for some maximal left ideal of A. Consider the set M plus AR is equal to M plus XR such that M belongs to M and X belongs to A. So M plus AR is left ideal of A. So X belongs to M plus AR, but R does not belongs to M. R does not belongs to M. So M is proper subset of M plus AR. So M plus AR is equal to A because M is maximal ideal. So M plus XR is equal to 1 for M belongs to M and X belongs to A. So M is equal to 1 minus XR. So M is equal to 1 minus XR. So M is regular and M belongs to M. So M is equal to A, which is not possible because M is maximal ideal of A. So our supposition is wrong. So X belongs to R. Not. X belongs to R if and only if 1 minus XR is regular for every X belongs to A. Second, R is equal to intersection of all maximal left ideal is equal to R such that 1 minus XR is regular for all X belongs to A. Third, we can prove that set of intersection of maximal right ideal is equal to R such that 1 minus Rx is regular for all x belongs to A, or R such, such that 1 minus Rx belongs to G for every x belongs to A. Intersection of maximal right ideal is equal to R such that 1 minus Rx belongs to G for every x belongs to A. Lemma 5. If 1 minus XR is regular, then 1 minus Rx is also regular. Suppose 1 minus XR is regular, so S is equal to 1 minus XR inverse. So we can write uh, S into 1 minus XR is equal to 1 minus XR into S is equal to 1, equation number 1. Then 1 minus Rx into 1 minus 1 plus Rs x is equal to, now multiplying 1 into this is equal to 1 plus Rs into x minus Rx minus Rx into Rsx. We write 1 minus Rx plus, we common out R and X. So we get S minus X R S. So 1 minus Rx plus, this is equal to 1 by 1. So R into 1 into X. So 1 minus Rx plus Rx is equal to 1. Similarly, we can prove that 1 plus Rs x into 1 minus Rx is equal to 1. So 1 minus Rx is regular, and now S is equal to, we take 1 minus Rx inverse is equal to 1 plus Rx plus Rx square plus up to infinite, and this is equal to 1 plus R common out and Rx common लिए, तो Rx common 1 plus Rx square plus up to infinite. So this is equal to S. So 1 plus R S x. So S is equal to 1 plus R S x. We complete the proof. Now R is equal to intersection of maximal left ideal is equal to intersection of maximal right ideal. Definition: semi-simple. A Banach algebra A is said to be semi-simple if R is equal to 0. Theorem: every maximal left ideal of A is closed in A. We have to prove every maximal left ideal of A is closed in A. Proof. Let M be a maximal left ideal of A. Suppose M is not closed, so M is proper subset of M closer. Now M is left ideal, so M closer is also a left ideal of A. So M is proper subset of M closer, proper subset of A. This is not possible, so M must be closed because M is maximal ideal of A. So every maximal left ideal of A is closed in A. Next theorem. The radial R of A is proper closed two-sided ideal of A. R is equal to intersection of maximal left ideal is equal to intersection of maximal right ideal. Next theorem. Let I be a proper closed two-sided ideal of A. Let I be proper closed two-sided ideal of A. Then A by I is Banach algebra with identity 1 plus I. A by I is Banach algebra with identity 1 plus I. We know that A quotient I is equal to x plus I such that x belongs to A. We also know x plus I plus y plus I is equal to x plus y plus I, and alpha into x plus I is equal to alpha x plus I. X plus I into y plus I is equal to xy plus I. So A quotient I is a vector space. Now A quotient I is A quotient I is Banach space with respect to norm defined by norm x plus I is equal to infimum of norm x plus I where I belongs to I. Now x plus I into y plus I into z plus I is equal to x plus I into y plus I into z plus I. Now x plus I into y plus I into z plus I is equal to 1 x plus I into y plus I into z plus I. This is associative property. X plus I into y plus I plus z plus I is equal to x plus I into y plus I plus x plus I into z plus I. We multiply x plus I into y plus I and x plus I into z plus I. This is distributive property, and alpha x plus I into y plus I is equal to alpha into x plus I into y plus I is equal to x plus I into alpha into y plus I, and x plus I into y plus I is equal to y plus I into x plus I. This is commutative. Norm x plus I into y plus I is less than or equal to norm x plus I into y plus I. Separate norm આપીએ ત્યારે less than or equal to. Let norm x plus I into y plus I is equal to x into y plus I. We use this, and now definition of norm x plus I, we use this infimum of norm xy plus I such that I belongs to I. So, and now x into y plus I is equal to x plus I1 into y plus I2 such that I1 I2 belongs to ideal and is less than or equal to infimum of norm x plus I1 into norm y plus I2, because we use this property norm x plus I into y plus I is less than or equal to norm x plus I into y plus I. And now give both, and now expansion this infimum of x plus I1 where I1 belongs to I into infimum of y norm y plus I2 where I2 belongs to I, and this is equal to norm x plus I, and this is equal to norm y plus I. Hence norm x plus I into norm x plus I into y plus I is less than or equal to norm x plus I into y plus I. Hence this. Hence, a quotient I is commutative Banach algebra. Now, 1 plus I into x plus I is equal to x plus I into 1 plus I is equal to x plus I, and norm 1 plus I is equal to infimum of norm 1 plus I such that I belongs to I is less than or equal to norm 1, because 0 belongs to I is ideal, and this equal to 1, that is norm 1 plus I is less than or equal to 1, equation number 1. Now norm 1 plus I is equal to norm 1 plus I square, because 1 plus I square is equal to, we write 2 times 1 plus I into 1 plus I, and this is equal to 1 into 1 1 and plus I. So 1 plus I square is equal to 1 plus I, and take both the side norm. So 1 plus I is equal to norm 1 plus I square. Now norm 1 plus I into 1 plus I, and give the separate norm less than or equal to norm 1 plus I into norm 1 plus I, and so norm 1 plus I is less than or equal to norm 1 plus I, so 1 into this is less than or equal to norm 1 plus I into norm 1 plus I. So 1 is norm 1 plus I is cancelled out. So 1 is less than or equal to norm 1 plus I. Equation number 2. From equation 1 and 2, we get norm 1 plus I is equal to 1. Hence, a quotient I is commutative Banach algebra with identity 1 plus I. Hence the theorem. Theorem: a quotient R is a semi-simple Banach algebra since R is a closed ideal in A, and A quotient R form a Banach algebra. Now definition: a map phi from A to A quotient R as phi of x is equal to x plus R, where x belongs to A, and phi of x plus y is equal to phi of x plus phi of y, and phi of x alpha x is equal to alpha phi of x, and phi of xy is equal to phi of x into phi of y. Phi is homomorphism. Phi of x is equal to phi of y. So x plus r is equal to y plus r. So x minus y plus r is equal to r. So x minus y is equal to 0. So x is equal to 0. Hence phi is 1 1 and on 2. So phi is an isomorphism from A on to A by A quotient R. So every maximal left ideal of A corresponding to a maximal left ideal in A quotient R. So R is equal to intersection of maximal left ideal in A. So phi of R is equal to intersection of M dash, where M dash is a maximal left ideal in a quotient R. So R is equal to intersection of maximal left ideal in A by R. Hence A by R is a semi-simple. Now we have to prove M. If M is maximal left ideal in A, then A by M is a division algebra. Definition: division algebra. Every non-zero element is regular. Proof: M is maximal left ideal, so M is closed subset of A. Hence A by M is a Banach algebra. Implies x plus M belongs to A by M and x belongs to A. So x plus M is not equal to M and x belong is and so x is does not belongs to M. Then M union x is a left ideal in A. M is proper subset of M union x subset of A. That is, M union x is equal to M plus alpha x, where M belongs to M and alpha is scalar. This is ideal generated by M union x. But M is maximal left ideal in A. So M union x is equal to A. So M0 belongs to M and alpha 0 belongs to A, such that M0 plus alpha 0 x is equal to 1. So M0 plus alpha 0 x plus M is equal to 1 plus M. So alpha 0 x plus M is equal to 1 plus M. M0 belongs to M, so we write M. And alpha 0 M plus x plus M is equal to 1 plus M. So x plus M is regular, not. Instead, M union x we can write I, where I is an ideal generated by M union x. Thank you.